We're looking at a very commonsensical law. So I would like to explain it this way using this. Okay, we have a closed container. Imagine that we have a closed container. It is filled to the maximum. At one end, supposingly we have a opening. Okay, suppose we have an opening. And other end we have another opening. Now, a very simple commonsensical question to you guys. Remember, this is incompressible. Say we have the capacity is 10 liters. Now, if I happen to pour in, say 4 liters of the same liquid. For this to happen, how much liquid should I remove? For pouring in 4 liters into this already filled container, and the fluid is incompressible. That is, you can't fit in more basically. You can't, like air can be compressed, a pillow per se can be compressed, a toy can be compressed, but this can't be. Okay, if this is the scenario, how much liquid should I take out so that we are able to fill in 4 new liters? Right? 4 liters. You guys agree? So basically, let me not take 4, let me take some 2 or something. So basically, first what should I do is I should take out 2 liters of water or liquid over here, whatever this liquid is, and it will give space for new 2 liters to come in. Do you guys agree? Do you agree for this? Do you agree to this? Do you agree this representation? That's what I meant. So this is out, this is out, and this is in. Can I tell this volume of liquid is in and this volume of liquid is out? Can I tell that? And what is the relationship between this two? And after this process, we still have filled container. So they have to be correct. They have to be equal. And we know that volume is given by what? Area times of depth. So if I consider this, I think you guys will be able to, let me put it here, AI. And this is AO. So these are your area of cross section. If AI and AO represent the area of cross section, we have AI times depth, say xi or delta xi, and this is delta x naught. AI delta xi is equal to a naught into delta x naught. Is that correct? Now I'm going to divide delta t both the sides. So what do I have? AI delta xi by delta t is equal to a naught delta x naught by delta t. And what is this? This represents velocity, and this represents velocity. What kind of velocity? We will talk about all of that, but with this, can I tell one statement? Rate at which fluid comes in is equal to rate at which the fluid goes out. Is this correct? Is this statement correct? The rate at which I'm filling in the tank, at the same pace the liquid should go out. Only then this particular condition, that the maximum capacity, it's always full, the container is always full, is satisfied. That is, it's always maximum, it's up to its maximum capacity if this condition is satisfied. Okay, so basically this is your equation of continuity, right? I'll relate it to the actual concept, but if this is commonsensical to you guys, that's your equation of continuity for fluid. So basically what it tells is if you have a pipe, right, and it has incompressible fluid flowing through it, okay, then the amount of water coming in one section has to be equal to the amount of water going out in another section. And if you do a bit of math, your A1, V1, where A1 is your cross section at one end, A2 is cross section at the other end. It need not be ends, anywhere in the between. You can imagine that this is very long pipe and we just taken two cross section at two different places. V1 is the rate at which the liquid is flowing in at A1, and V2 is the liquid at which the liquid is flowing in or out at A2 cross section. And this product is constant. So that's the entire idea. Okay. So I have a diagram for you guys over here. Actually, let me take a second and erase all of this. Okay. So yeah, let's have a look at this. Imagine that this is not infinite, but it's a very long tube, or at least this is not the end or this is not the start. It can be, but let's imagine that it's pretty long tube. Okay, we're considering point A and point B. Point A, we have this particular cross section, and point B, we have this particular cross section. Okay, so this is a cross section. Now, if there is this amount of water coming in and the molecule along this length has a velocity of v1, okay, an equivalent amount of water is coming out and the molecules at point B had to move to new point B dash, for example. Here they have moved to point A dash, and this depth is delta x2, and this velocity is v2. Okay, so this is the scenario. Okay guys, now can I tell from figure delta x1 is equal to v1 delta t and delta x2 is equal to v2 delta t? Do you guys agree? x1, x2. Speed is equal to distance by time. So distance is equal to speed into time. Can I tell this? Now, mass m1. So through, that is fluid via A1 or point A, not point A actually, via A1. Okay, at point A we have A1. If M1 represents that, and this is represented by A2. Then we have M1, which is equal to mass is equal to density times of volume, and density times of volume here is given by area into delta x1, which in turn is equal to A1 into delta x1 is V1 delta T. Similarly, we have M2 is equal to rho A2 V2 delta T. Okay. Since we are looking at an incompressible fluid, so as we are dealing with incompressible fluid, can I tell that M1 should be equal to M2, and we have rho A1 V1 delta T should be equal to rho A2 V2 delta T, right? It has to be. I mean, we just discussed that at the start. Delta T, rho and rho will get cancelled. We have A1 V1 is equal to A2 V2. And that's that. Okay. So, yeah. So, you have this derivation over here in a very neat manner with written statements and everything that I'll show it to you guys. So conclusion is that the equation tells us that the speed is higher where the tube is smaller and lower where the tube is wider, right? So if in this case, so in our diagram, A1 is lesser than A2. So if I rearrange, V2 will be given by A2 into V1. So this is a less than 1 case because A1 is less than A2. This value will be less than 1. Therefore, V2 will be less than V1. Okay, you can see over here. Here we have a smaller tube. Here we have a bigger tube. I mean, it's wider. So here the velocity has to be slower than this. And that's that. Okay, what else do we have? That's it. So volume flux or the fluid rate, the product of AV, which has a dimensions of a volume per unit time is, okay, I don't remember what exactly I meant over there. Mass flow rate. If the density R of density rho of a fluid is uniform, we can multiply equation by the density to get the mass rate. Okay, this is nothing but mass in is equal to mass out. Okay, not a big deal. All this is okay. Okay, guys. Anyways, for me, I can't just read through and explain things. It has to come naturally. So what we looked at is a very commonsensical law. If we have a scenario wherein we have a pipe filled with an incompressible fluid, for the water or for the liquid to just keep flowing, you have to make an equal amount of liquid to come out so that the same amount of liquid can come in, right? And that's your equation of continuity of fluid. That's it. Okay, so you guys can look at what to write in this screen and from the screen. This also is only for the sake of explanation. The actual derivation I'll show it to you after this. Okay, you guys can look at the actual derivation. I mean, you need to write all of the statements and everything.